This video is on volume of solid revolution using the shell method. And so here I have the function y equal to negative x minus 3 squared plus 6. And this is the line y equal to 3. And I'm going to revolve this region right here around the line y equal to 2.5. And then we'll get a solid revolution like this. And I want to find the volume of this solid revolution. And this is our yellow region again. And so first what we need to do is find the points of intersection right here. So we need to find this point and we need to find this point. So we can set this equation here, the equal to 3, and then solve for x. And so here's our equation right here, and then simplify by subtracting 6 from both sides and then multiply both sides by negative 1, and then we end up with this. And then take the square root of both sides, then we get x to be plus or minus the square root of 3 and then plus 3. So the points of intersection are the square root of 3 plus 3 for the x and then 3 for the y. And then the point of intersection that's right here will be negative square root of 3 plus 3 and then y is 3. And so here are the points of intersections again. And then now let's revolve it about the line y equal to 2.5. And then this is what the solid revolution would look like. And then and so notice that we have a hole right here in the middle. And now we're going to use the shell method. And so I'm going to divide this solid revolution right here into 6 shells, cylindrical shells, like this. And then we're going to find the volume of each shell. And then now I'm going to calculate the volume of each shell and then add the volumes together. And so for the 6 shells, the volumes of the 6 shells is 75.12, and therefore the volume of the solid revolution is approximately 75.12. And to get the exact answer for the solid revolution, instead of 6 shells, we're going to divide it into an infinite number of shells. And one of the shells would look like this. So let's call this the ith shell. And so for the ith shell, we have been the distance from here, from the axis of revolution to here, that's the radius of the inner shell. And then the distance from here to here will be the radius of the outer shell. And so right in the middle right here, let's call it y sub I star. So right here. And so the distance from the x-axis to here would be y star. The distance from here to here is 2.5. And so the radius for this, the average radius for this ith shell will be y star, y sub I star, minus 2.5. And then the height of this shell right here, this bounded on the left side by this curve, and is bounded on the right side by this curve. And then if we take this equation right here and solve for x, then we get x equal to the square root of 6 minus y plus 3, and then x equal to negative square root of 6 minus y plus 3. And so the negative square root of 6 minus y plus 3 is this part. And then the square root of 6 minus y plus 3 is this part. And so I'm going to call this g of y, and then I'm going to call this part f of y. And so the height of this shell right here is going to be f of y sub I star minus g of y sub I star. And so right here is y sub I star. So f of y sub I star is the distance from the y-axis to this point right here on the graph, which is the graph of f of y. And then g of y sub I star is the distance from the y-axis to this point, which is the graph of g of y. And so this point right here is the point. This point right here will be the distance from here to here will be g of y sub I star. And so this will be the height of the ith shell. And now we can find the volume for this ith shell. The volume of a cylindrical shell is 2 pi times the average radius times the height times the thickness. So we found that the average radius for this ith shell is y sub I star minus 2.5. The height for this ith shell is f of y sub I star minus g of y sub I star. F of y sub I star is the square root of 6 minus y sub I star plus 3, and then g of y sub I star is negative square root of 6 minus y sub I star plus 3. And so we end up with 2 times the square root of 6 minus y sub I star. And then the shells, let's make all of them, the thickness, let's make all of them the same. And so the recorded the original region ranges from here to here, which is 3 to 6. And so we make the thickness of each shell 3 dividing by the number of shells. And let's make them all the same. And let's call it delta y. And so the volume of the ith shell will be 2 pi times the average radius, and then times the height, and then times the thickness. So once again, the thickness, it's since they're all the same, then we don't need to write delta y sub I, since all thickness are the same. So this is the volume of the ith shell. And so the volume of an infinite number of shells will be the integral from 3 to 6. From 3 to 6. And then here's the average radius, and here's the height, and here's the thickness. And then we can use numerical integration right here. And then if we use numerical integration to evaluate this definite integral, it'll come out to be 74.003. And now let's look back at the volume of the 6 shells. When I divided this solid of revolution into 6 shells, the sum of volumes of the 6 shells was 75.12. And here's the volume of the solid of revolution with an infinite number of shells is 74. So we can see that they're very, very close. And that's the end of the video.